In the world of real numbers, 1 is a special number. 1 is a special number because if you take the number 1 and you multiply it by any real number, you get that same real number back again. It's kind of like what 0 did for addition, 1 does for multiplication. 1 is what's called the multiplicative identity. The multiplicative identity is the number you multiply by anything to get that anything back again. It also allows us to talk about multiplicative inverses. That is, if you take any number, can you find another number that when you multiply them together give you the multiplicative identity? When you multiply A and B, well, perhaps you've worked with real numbers long enough to realize that B has to be what we call the reciprocal of A, right? If you take A times 1 over A, then you always get 1. Now this works for every value of A except 0, so I better, maybe point out here that A is not equal to 0. But otherwise, this works. What we want to do now is do a similar thing for matrices. That is, if I'm given a matrix, can I find an inverse matrix? Can I find a way of essentially dividing by it? Because if I multiply by a reciprocal, I'm essentially dividing. If I multiply by half, it's the same as dividing by 2. And I want to be able to do that with matrices. So what we're doing, first of all, is I'm going to come up with the notion of a 1. I mean, for the 0, we had a 0 matrix. I want to get an identity matrix now. So let me slide up a little bit here. So I want to start with some matrix A. It doesn't have to be m by n. It doesn't have to be square, but it usually is square with the stuff that we're doing. But start with a matrix A. Let's just say it's m by n. And I want another matrix, which I'm going to call I, for identity, so that, okay, now how come my pen isn't writing very well? So that A times I is equal to A. I'm also going to want to do it on the other side, but let's just write it this way for the moment. Notice that if A is m by n, and the result here is m by n, this matrix here, in order for this multiplication to work, first of all, has to be n by something, right? Because this number and that number have to be the same in order for the multiplication to work. But then this number is the size of this, so this has to be n by n. So this identity matrix has to be square, right? If I do it on the other side, let me move over here. If I said I also want I times A to equal A, and this is m by n, the result, of course, is m by n. Let me slide over a little bit. So this side is m by n. Then I has to be something by m, because those numbers have to be the same. And this tells me what it has to be. It has to be m by m. So either way, whether it's going to be multiplied on the left-hand side or multiplied on the right-hand side, like this one over here, the identity matrix turns out has to be square. Okay. Well, we can motivate this lots of different ways here, or we can just kind of write it down, but I want to motivate it a little bit here. So suppose let's start off with like a 3 by 3. So A, B, C, D, E, F, G, H, I. And I'm going to multiply by something. And I want to end up with ABC, D, E, F, G, H, I. So what I'm looking at here is, so just focus on this A right here. I'm going to take this column and multiply it by this, 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 and then add them together and end up with A. It's like the simplest way I can think of doing that is just doing 1, 0, 0, right? Because they then have A plus 0 plus 0. That would give me that A. Likewise, the D plus 0 plus 0, D plus 0 plus 0, that gives me this D. And the G plus 0 plus 0 gives me that G. So this right here definitely works for making that first column work. Right? Then I look at the BEF. So I'm going to take this column times this row and work my way down. And the first thing I need to end up with is a B. So the B comes from right here. I need a 1 right here so that when I multiply by that B, I get B back again. But I don't want anything here and I don't want anything there. So I'd have 0 plus B plus 0. Likewise, move down 1, I'd get 0 plus E plus 0. That gives me that E. And likewise, G plus H, 0 plus H plus 0 is that H. And similarly, I want a 0, 0, 1 on the last one. This right here, this matrix right here, is what's called an identity matrix. And it is the identity matrix that's a 3 by 3 identity matrix. So I would call this I sub 3. Right? For each value of n, you have an identity matrix. In fact, I got the book kind of opened up here. This would be the 1 by 1 identity matrix. It looks just like the number 1. This would be 2 by 2, 3 by 3, and the 4 by 4 identity matrix. Notice there's 1s on the diagonal and 0s everywhere else. Each of these is called an identity matrix. Now, we need to look at some properties of identity matrices. Actually, the property that I really want to look at is Theorem 1.4.3. This is, again, looking at the book. Essentially, it says if you've got an n by n matrix A, and you put it in reduced row echelon form, to me, this doesn't really need to mention A. If you've got R, it's in row echelon form. It's an n by n matrix. So here's an n by n in reduced row echelon form. Then either R has a row of all zeros, or R is an identity matrix, right? Well, easy enough to prove in that if you think of this, if it's n by n, so it has n rows. If every row has a leading 1, then you can't have 2 leading 1s in the same column. So the leading 1s have to be in all different columns. You only have n columns. So every row has a leading 1. Every column has to have a leading 1. And they have to go diagonally downward. So you have to have 1s on the main diagonal here. And since it's reduced row echelon form, above and below any of those leading 1s has to be all zeros, which makes it an identity matrix, IN. On the other hand, if you have fewer than n leading 1s, then you're going to have a row that doesn't have a leading 1 in it, which means you've got a row of all zeros. So either you got a row of all zeros, or the reduced row echelon form is an identity matrix. This is when you, for n by n, if it was rectangular and not square, then this theorem doesn't apply. Okay. So the next thing we want to do with this identity matrix is to talk about inverse matrices, essentially reciprocals.